Hey guys, welcome back. We know how to join datasets in Pig, and writing a join statement is very easy. But writing an optimized join statement in Pig requires understanding of what happens behind the scenes when Pig executes a join instruction. Knowing the details will help you write optimized join statements. This lesson will teach you different ways to optimize the performance of join queries in Pig. This is a very important lesson. We have seen candidates grilled in interviews in the concepts that we are going to discuss in this lesson. But you don't have to worry. We will go through step by step in great detail and help you understand every single concept. This is an important lesson not just for interviews. If you end up using Pig, I guarantee you will use the concepts that you learned from this lesson in your day-to-day job in your Hadoop environment. Let's see what we are going to learn today. We're going to learn how joins work in Pig. Next, we'll talk about three kinds of joins in Pig: fragment replicated join, skew join, and merge join. Each type of join offers a key performance benefit. Let's say we would like to join the stocks and the dividends data set on the symbol and date column. Let's first understand how a join is implemented behind the scenes with no optimizations. When I call out for steps, just follow the numbers, okay? Step 1. The stocks and the dividends dataset are read by individual mappers. Step 2. Each mapper emits a key value pair. The key is going to be the join key. In our case, it is the symbol and the date, and the entire record will be the value. Step 3. Shuffle phase will sort the records by key and send the records to the appropriate reducer. Step 4. Records from all tables except for the last table in the join will be loaded in memory on the reducer side, which means, in our case, if you look at the instruction here, the records from the stocks dataset will be loaded in memory on the reducer side. Step 5. Records from the last table are the rightmost table in the join class. In our case, the dividends dataset will be streamed to the reducer, meaning the join process will start as the records are coming in from the rightmost table. In our case, again, it's the dividends dataset. Step 6. As the records for the rightmost table come in, the reducer will cross the records from the stocks and the dividends and apply the join condition and will derive the result set. Now, look at the illustration on the screen. There is a small tweak we can do to optimize the join. Can you think of what it is? From step 5, we know records from the last or the rightmost table in the join class will be streamed to the reducer, and the records from the other tables will be loaded in memory or cached in memory on the reducer side. Since memory is a limited resource, we should always want the smallest table in memory and not the biggest table. Also, storing the smallest dataset in memory will be a quick operation than storing the biggest table in memory. Because to load the biggest table in memory, you have to wait for all the records from the biggest table to arrive on the reducer side so that you can cache all the records in memory. With that in mind, we also know that the stocks table is the biggest table of the two tables in the join statement. So immediately there is a chance for optimization. Let's change the position of both the tables in the join instruction. Just look at the highlighted instruction here. Now stocks is the rightmost table, and the records from the stocks dataset will be streamed to the reducer, and the records from the dividends dataset will be loaded in memory on the reducer side. This way, this join instruction will be much more efficient than this join instruction right here. Does that make sense? Okay, let's execute this join instruction in our cluster. I've already logged into the cluster. Let me type in pig. I have now entered the grunt shell. Let me copy the load instruction first for stocks. Stocks is now loaded. Let me copy the instruction to load the dividends dataset. Dividends is now loaded. Now let's copy the join instruction. I don't want to print all the records. I just want to print the top 100 records. So I'm going to say limit 100, limit join symbol 100, dump, limit 100. So pig is doing its usual stuff. It takes in the instructions. It would convert those instructions into MapReduce jobs, and it would execute the MapReduce jobs in cluster. Here is the URL for this application. So let's copy this URL. So the application is now running. As you can see, here's the progress. So the maps are now complete. So right now we have only one reducer running. And now all the records from the dividends dataset is now cached in memory on the reducer side, and the records from the stocks are streamed in, and the join is performed on stocks and dividends as the records from stocks dataset are streaming in to the reducer. So the reducer doesn't wait for the entire stocks dataset to come to the reducer side. And this is the advantage of having the stocks dataset as the rightmost dataset, because the dataset that is specified on the rightmost side will be streamed to the reducer, providing a much more optimized join. There you go. The job is now complete and it is successful. And here is the result set. Perfect. So now you know just changing the position of the datasets in a join statement can create a big difference in terms of performance. So that is why I was saying it is important to know how join works behind the scenes. Without that knowledge, it is hard to execute an optimized join. Now that we understand how a basic join works behind the scenes, let's move on and look at a special kind of join, the fragment replicate join. Sorting is an expensive operation. An extensive sorting occurs when you send the values from individual mappers to the reducers. I'm referring to the shuffle phase. So the idea is if you can avoid the shuffle phase, you can get better performance. But you cannot avoid the shuffle phase when you have reducers. So the only way you can avoid the shuffle phase is to eliminate reducers, which means performing the entire join operation in the map phase itself. This is called a map-only join or fragment replicate join. This is the essence of fragment replicate join. And it is only possible when one of your dataset is tiny and it can be fit into memory. The syntax to perform the fragment replicate join is very simple. At the end of the join instruction, all you have to say is using replicated. And this means Pig will execute this join as a fragment replicate join. Now let's go over the steps. Step 1. A new map-only MapReduce job is launched, and this job will prepare the dataset on the right-hand side, in our case the dividends dataset, and copy the dataset into HDFS. This is a preparatory step to make the dividends dataset available in the distributed cache. The concept of distributed cache is simple. Anything you add to the distributed cache will be copied to all the nodes running the mapper or reducers for the job. Step 2. The second map-only MapReduce job add the entire dividends dataset into the distributed cache. So the dividends dataset is available on all nodes for all the mappers locally. Step 3. The second map-only MapReduce job does the actual join. It loads the dividend dataset which is available locally on all its mappers into its memory from the distributed cache. Step 4. The second map-only MapReduce job read the large stocks dataset, and each mapper process an input split of the stocks dataset and perform the actual join operation with the dividends dataset. Since the stocks dataset is fragmented between mappers and dividend dataset is replicated to all the mappers, this join is called the fragment replicate join. And writing this join is very simple. Just say using replicated at the very end of your join instruction. The rightmost table, in this case the dividends dataset, is pushed to the distributed cache and loaded into all the mappers in memory. Now let's execute this join instruction in our cluster. Here's the instruction. Let's also limit the output to 100. Limit 100. Oh, there is a typo there. So let's fix that. There you go. So let's wait for the execution to complete, and then let's review the job. So here's the output from our fragment replicated job. Let's go back to this job execution and let's review the job. The first thing you would notice is the big features used in the script, replicated join. And this confirms that Pig is introducing replicated join optimization to the execution. Let's move down a little further. Now in here, this is the second map-only MapReduce jobs. As you can see, the mapper is processing the stocks dataset. And I know that because the number of splits is 4. Stock dataset is big and it has 4 splits. And in this job, the dividends dataset will be loaded in memory from the distributed cache on all the mappers, and the join is executed between the records from the stocks dataset and the dividends dataset. And each mapper will process the stocks record from its own split. And at the very end, we see the job as success, and then the output is printed. Let's also go and check the application UI. 2 applications that got created and executed for our fragment replicate join. Let's look at the first application. The first thing you would notice is the number of mappers is 1, and the more important thing is the number of reducers is 0. And this job is actually a map-only MapReduce job, which is responsible to move the dividends dataset into the distributed cache. Now let's go back. Let's look at this application. This application is again a map-only MapReduce job responsible to do the actual join between stocks and the dividends. As you can also see, the number of reducer is 0. The number of mappers is 4 because it processed 4 input splits from the stocks dataset joining with the dividends dataset. Now let's go back to our illustration. So in the illustration, as we have already seen, each mapper will have the entire dividends data set in memory. And each mapper will read corresponding input split of the stocks dataset and will do the join. Now, I have an interview question for you. Looking at this illustration, tell me what kind of join is not possible with this approach. Any guesses? So the question is, which kind of join is not possible with the fragment replicate join? Let's take inner join first. Inner join is straightforward. As the records from the stocks dataset is read, it will be joined with the dividends dataset, and if there is a match based on the join condition, the record will be added to the output. Let's now talk about the left outer join. Stocks dataset is in the left-hand side, and each record from the stocks will be scanned against the entire dividends dataset. Since the entire dividends dataset is available in memory, for the mapper, if there is a match, the matching dividend record will be included in the result of the join, or nulls will be substituted for dividend columns. So that is simple too. So left outer join is possible. Let's now talk about the right outer join. In a right outer join, you take a dividend record and you're trying to find whether there is a matching stock records for the dividend record. Let's take mapper 1, which is processing input split 1 from stocks dataset. If you happen to find a matching stocks records in a mapper for the dividend record, great. But what if you don't find a matching stock record in the mapper for the dividend record? In that case, you cannot simply substitute null for stocks, assuming stocks doesn't have a matching record for the dividend record, because mapper number 1 is only processing input split 1. And may not have the matching stock record, but mapper number 2 or 3 might have a matching stock record for the dividend record. Hence, for that reason, right outer join is not possible with fragment replicated join. And for the same reason, full outer join is also not possible since it is a combination of left and right outer join. Another interview question. Ready? We know the rightmost table is loaded into memory in fragment replicate join. But fragment replicate join can be used with more than two tables. So the question is, when you use more than two tables in a fragment replicate join, which table will be loaded into memory? Any guesses? The answer is, in that case, all the tables except for the first or the leftmost table are loaded into memory. I got one more question. Ready? We know the table from the right hand side will be loaded into memory. So now what happens when you don't have enough memory or by mistake you put the biggest table in the rightmost position? In that case, the pig script will error out during runtime. So make sure the dataset can be held in the memory. There is no hard-cut number for this. If you have a lot of main memory, you can hold relatively large datasets in memory. If not, it will be difficult. You can also control the maximum number of bytes that you allow to be replicated using pig.join.replicated.max.bytes property, which by default is set to 1 GB. In order to avoid replicated joins on large relations, pig will fail automatically if the size of the relation or dataset to be replicated is greater than the allowed maximum limit set by this property, pig.join.replicated.max.bytes property, which is by default set to 1 GB. That is it for the fragment replicated join. So far, we have looked at how joins work behind the scenes in pig. We also looked at fragment replicated join, and we also covered a lot of potential interview questions with it. It's a very important lesson. Let's conclude the part 1 of pig optimization. In the next lesson, we'll look at 2 more join optimizations in pig: skew and sort merge join. See you in the next lesson.